So, hello guys. So we will be tackling another lesson which is known as the fluid mechanics. Ito, that's not. Yeah, dito. Fluid mechanics. So, fluid mechanics. So, we have dealt about the mechanics. We have dealt mechanics, and now we will be dealing now with a little more complicated, which is the fluid mechanics. So, sir, excuse me, what does fluid mechanics do? So, we all know that mechanics are objects at rest. Okay, so objects at rest. Now we will be dealing with fluids at rest, or meaning to say that those fluids are within a container. Okay, within the container. So some of these fluids are not just resting per se, but we will be also dealing with the fluids that are in a little bit in motion. Okay, but we will not be dealing about the motion of the fluid, but rather the area and the fluids that are passing through that area. Okay, so meaning to say that some of the fluids that we will be discussing doesn't involve the fluid per se. Okay, so we will be discussing about the area, and what specific type of fluid that passes through those areas, or within the bucket, or within the container itself. Okay, so that is what the fluid mechanics we will be dealing for today's lesson. Okay, so fluid mechanics. So let's start with the first one, which is the mass density. Okay, so when we talk about mass density, yes, it is the mass. And the one that we will be dealing here is the mass, and additional here is the density. So when we say mass density, it is how much volume are within the mass of our fluid. Okay, so mass density is the mass per unit volume. So it is well represented by a Greek symbol rho, or which we can call this rho as the mass density, which is in mathematical equation or formula is equivalent to kilograms. Kilogram all over cubic meter. So if it will be written in a formula, it will be written as rho, or our mass density is equivalent to mass over volume, where m is our mass and v is our volume. Mass over volume, mass density. Okay? So that is our mass density. Next, we will be having the specific weight. So this is not difficult to understand like the mass density is. Specific weight is known to be the weight per unit volume. So it has a Greek symbol of gamma, yung letter Y. It is a little bit of letter Y. And the specific weight has a unit of Newton per cubic meter. So its formula is written as gamma, or specific weight, is equivalent to weight per volume, or equivalent to mass density times the gravity. Okay, sir. Question: how is it possible that weight over volume is equivalent to our mass density multiplied to gravity? Okay, so let me show you this one, guys. Okay, so we have here the mass density as mass per volume, or equivalent to our rho. Okay, so rho. Okay, so if we both multiplied here to gravity, so this mass times gravity is equivalent to weight. Okay, equivalent to weight. So what happened to our volume? Nothing happened to our volume. It is just stayed the same. Okay, so with this, our specific weight all over volume is equivalent to our gamma. Or meaning to say, this gamma is equivalent also to our mass density multiplied to gravity. Okay, so if we both multiplied the mass over volume by to gravity, and our rho, or our mass density to gravity, we can get the weight. Okay, weight all over volume, or simply rho times g. Okay, so this is how gamma is equivalent to our rho multiplied to gravity. Okay, so I hope this one, guys, is clear for you. Okay, so I hope this is clear. Okay, so let's move on to the next. Okay, so specific gravity. So specific gravity is also known as relative gravity. Ratio of the density of a substance to a given reference material. So normally, and in most cases, the reference material used is water. Okay, so what's better way to have a reference fluid? What is better reference fluid than water? Okay, so water is very versatile. You can find it anywhere. You can find a water in a room temperature. You can find also a water that is below 0 degrees, or meaning to say it's ice. Okay, so water can also be used as reference material, reference fluid that has a boiling point, okay, which is the 100 degree Fahrenheit. Okay, so in most cases, water is the boiling point of the water varies from its pressure. Okay, so we will be discussing that in our future lessons. Okay, so but for now, we will be discussing water as our reference material. Okay, so normally we have a water at 4 degrees Celsius, or 39.2 degrees Fahrenheit. So specific gravity often used in the applications of checking the concentration of solutions and substance reactions. So in mathematical formula, we will be having SPGR, specific gravity. It's equivalent to our raw subs over our raw of water. Or in other cases, we will be using the gamma and gamma of the water, gamma of the substance and gamma of the water. So either of the two we can use, which is also equivalent to our SPGR. Okay, so specific gravity is equivalent to substance mass density of the substance all over the substance of the water. The mass density of the water, or in other cases, specific weight of the substance all over the specific weight of water. Okay. Okay, so pressure. So pressure. So basically, when we talk about pressure, there is always pressure on the water. So as let's go to the example of the ocean. As you go deeper, the pressure increases. For it has a greater force and a greater area. Okay. So if you are basically on a tank, when you're on a tank or in a container, so when you reach the bottom, the bottom of the tank, it has a pressure that can prevent you from floating. But when you have a force or a area or an area that has a as wide as the ocean, so the pressure on that is much greater. So just like the Titanic, so as it submerged, it has its component, or even the mighty Titanic is being swallowed by the water. Okay, so when we talk about pressure, this is defined as the ratio of the force exerted per unit area. So the area we are talking about is the area where the force is exerted, and in other terms, this is the area where force is perpendicular to it. So written in a mathematical equation, P or pressure is equivalent to force over area. Force is F is force where in newtons, and A in area is in square meters. And for pressure, it is in Pascal or PA. Guys, I have to reiterate this one. The area we are talking about in this is the area where the force is exerted, or in other terms, area where force is perpendicular to it. Okay, so guys, when we talk about this area where force is applied, okay, so when we talk about this hand, you will find that the area of this hand, the area that covers this hand, is up until to its fingertips. Okay? Up until the area of its fingertips, or in each finger. Okay? So not just this palm, and or the spaces between the fingers. It is not just the spaces on the fingers will not be counted, or will not be considered part of the area of the hand. Or in some cases, we're not just going to use the area of the palm. So meaning, when we applied force, the area that covers the hand is within each fingers up until to the fingertips. Okay. So, and it is perpendicular, meaning the force exerted, let's see. The force exerted is in here. The force is going up to this direction, and the area is this. Okay, so as you can see, the area is in front of you, and the force is also coming in front of you. They are not parallel; they are perpendicular. So the area is this one, and the force is this one. Okay, so that is perpendicular, and we will be seeing that in our next slides. Okay. So again, pressure is equivalent to force over area. We have a unit of pressure. We have a unit of pressure which is in Pascal. Okay. So hydrostatic equilibrium. The hydrostatic balance in the fluid at rest is what we know as the hydrostatic equilibrium. This implies that the sum of the forces in one direction must be equal to the sum of the forces in its opposite direction. So again, that's why it is called equilibrium, balance, hydrostatic equilibrium. So in this example, we will be having this illustration sooner. Okay. So we have here the sum of the forces equivalent to the force plus the force atmospheric pressure, and the force applied, or the force of the weight. Meaning we have a formula of PA, or pressure times the area, minus pressure of the atmospheric pressure times the area, and minus again to our rho GH times the area. Okay. So we have here 0 is equivalent to P minus P atmospheric minus rho GH. So we have canceled the area. So since they are in the same in the same location, having the same areas, that's why we have to cancel the area. So sir, why is it we have the same areas? Okay, so when we talk about equilibrium, it is the balance where sum of the forces in one direction must be equal to the sum of the forces in opposite direction. One direction to the opposite direction. So what better way to have these forces in one direction to the opposite direction? So it will be in the same place. Okay, so if it is in the if you have an open space like the ocean, or a lake or a river, open space yan. it's hard to predict or it's hard to compute for the area. Okay, and since it is not it is wide, it is broad. You cannot just assign a an area for each of the object. But for this, we will be having areas that are the same for they are in one specific location. For example, a drum. Okay, so water drum or water tank or water container. So they have the those areas are a little bit are smaller than the likes of the ocean. Okay, so sir, we have here a raw GH. So this is another form of our pressure. Okay, so this is another form of our pressure. Okay, so raw GH. Okay, so what's the unit of our raw? The unit of our raw is kilogram all over square cubic meter, which is mass over volume, right? And we have a unit of gravity of meter per second square, which is in fact, this will be in newtons, right? This will be in newtons. Okay, so sir, we have here a cubic meter. We have here a remaining cubic meter, which is newton all over cubic meter. We have here the remaining component, which is the H, or in meters. We can cancel this one out. We will be having a newton per square meter. Okay, so what is newton? It is a force. Okay, and we have here area, or simply our pressure. Okay, so don't be fooled by this, or don't be rattled that you have seen this raw GH. So meaning when we have raw GH, meaning it is pressure. This one is pressure. Okay? So yeah, so I hope guys you get this derivation of our raw GH. Okay, so we have here zero, or equilibrium, is equivalent to P, pressure, minus atmospheric pressure minus raw GH. Okay, so we have here a formula of P is equivalent to P atmospheric plus raw GH. So this is our formula. This is our formula for our hydrostatic equilibrium. Okay? So yeah, we just transpose the P atmospheric atmospheric pressure and the raw GH on the other side. So those two became positive, and then we just arrange it to a more suitable formula, which is the P, or nothing is negative, or nothing is in the negative side. So we have here P is equivalent to atmospheric pressure plus the raw GH. Okay? So yeah, Pascal's principle. So in fluid mechanics, Pascal's principle states that in a fluid at rest in a closed container, a pressure change in one part is transmitted without loss to every portion of the fluid and the walls of its containers. So transmitted without loss. Okay, so meaning that from one place to another, one location to another, all of the fluids are being transferred without any loss. So since all of the fluids in the walls of our container has also been taken, nothing's left behind. Okay, so that is Pascal's principle, transmission without any loss. Pero we all know that it is not possible to transmit all of the fluids without any compromise, um, without any losses. So this one, when we talk about Pascal's principle, this is ideally. Ideally, when we talk about ideally, nothing is, there is no external factors. So meaning when we talk about Pascal's principle, transmission without any loss, it is by far ideal in terms. Okay, so that's why it is called formula, theory. So it is based ideally without any external factors. Okay, so in here we have Pascal's principles transfer from one area to another without any loss. Okay, so when the force A applied, so meaning the fluids in here will flow in here, going here. So this force B will change direction. So if force A applied, then the force B here will go up. Okay. So when we on the same note, when you applied force B downwards, then force A will go up. Okay, so here is the perfect example of pressure that we are talking about a while ago, that force is perpendicular to the area. So as you can see, this is the area that we are covering. Now the force exerted, as you can see, force and area. Perpendicular ang dalawa. Okay, so when we talk about this Pascal's principle, when you applied force A downwards, meaning they have only one direction to go. The fluid will only have one direction to go, which is here in B. If force A applied downwards, then automatically our B will go upwards. Same goes for our force B. If it is applied downwards, then force A will go upwards. This is what Pascal's principle is saying, that that no loss or no loss for our fluids. So you can see, or you can witness this principle normally in hoses, like in hospitals. Transmission of the dextrose to the body of the patient, or transmission of the blood to the patient. Since you can say that there will be no loss, there will still be loss. There will still be minimal losses from the blood to water, or to any kind of fluid. Okay, so and we're just talking here about the ideal Pascal's principle. Okay, so we have here a formula here of force over area force over area is equivalent to force over area of A and B, meaning P, pressure of A, is equivalent to pressure of B. Okay. So yeah, so meaning we have greater force here with the little area, and we have minimum force here for a great area. Okay, so we will be dealing with this in our examples. Okay. So Archimedes Principle, Archimedes states that the upward buoyant force that is exerted on a body immersed is in a fluid, whether partially or fully submerged, is equal to the weight of the fluid that the body displaces. Okay, so it is like putting a rock in a cup or a glass, and that the rock and the force exerted is the same force the fluid exerts when the rock was submerged, or submerged partially or even full. Okay, so buoyant force is part of the Archimedes principle, that the force on an object is the same or equal to the weight of the fluid displaced by the object. So when we talk about Archimedes principle, this is what we call the submerging of the objects to our fluids, and that object that has a force or has a mass, the fluid gained also what it has, what what you have placed on it. Okay, so for example, on this water container. So if it since this is just an example, so nothing is placed in this. Nainom ko na, naubos ko na siya. Okay. So yan. So this bottle, this water, when you have put water in it and it is not on the same level as its opening. Okay. So you have placed water in it up until to the tip. Okay. Up until to the end. Flat out. Okay. And you place an object, let's say this as big as this mouse, Okay. So what do you think will happen? So automatically it will flows out because you have added an object. That is that can easily put the water out. Okay. Pero the question is how much water? How much water goes out? How much water? The same as the mass or the mass of our mouse. Okay, so that's what happened. That's how much water has gotten out of the container. Okay, so let's try to have this example. Let me show you this one, guys. Yeah. Okay. So please try to pay attention to this detail. So their water level. When it was placed, umangat ng konti yung ating water. So nagdagdag pa, tumaas. Okay. So guys, as you can see, it's still, yeah, it's almost pantay pa din. Almost pantay. For we have increased here 1 ton, 200, 250, 250, 500, 500. So meaning we have 1 tons na naidagdag dito. So what happened here is that when we put objects in here, it didn't fully submerge. But when it increase, the height it increases, also the same as the height increases of the water on this on the other side. So as you can see that from our Pascal's principle to Archimedes, they are both active in here. Okay, so we have added 1 ton. And maybe on this one, it also increases a ton. Okay, so the height increases also the same as the height increases on the other side. Okay, so Pascal's principle and Archimedes principle in one video. Okay, so let's move on. Next. Okay, so continuity equation. So in the study of mechanics, observation of materials and objects is easy. But when it comes to fluid mechanics, things will be a little different. Okay, so it will be a little different knowing that tracking or observing a part of a fluid is nearly impossible. So the fluid is the same as the energy, as it cannot just appear from it will not just appear from one point to another, or it will just be created, okay, or vanish into thin air. Okay, so for this one, we have area 1 and area 2, and we have volume 1 and volume 2. As you can see, volume 1 is slightly bigger or larger than our volume 2. Okay, and with this, our area 1 is also larger than our area 2. Okay, so we have here mass 1 and mass 2, but as you can see, guys, mass 1 and mass 2 will be equal. So meaning the volume of our area, volume 1 and area 1 will be equal to our volume of area 2 and volume 2. Okay, so we have here a formula of rho times the temperature and area. But as you can see, we will be just gonna cancel the temperature and the pressure. So since the pressure will be constant in here, meaning that we will be having a larger volume than our volume 1. Okay, so we have here the formula A1 V1 is equivalent to A2 V2. Okay, so last one is the Bernoulli Principle and the conservation of energy. So Bernoulli's principle is created by Daniel Bernoulli, the pioneer of the kinetic theory principle. So the Bernoulli's principle states that as the pressure exerted by the fluid decreases, the fluid's velocity increases. Okay, so this principle has been proven and seen using water hoses. Okay, so the Bernoulli principle, guys. Bernoulli principle. So the fluid decreases, the velocity increases. Okay, so sir, how does that possible? Okay, so as you can see, sino dito nagdidilig ng halaman? So some of you has experienced na maglaro, played with the hose, that it is just flowing normally. It is just flowing normally, but it happens that when you if you make the exit way of our water a little smaller than its usual size, so you will see that the velocity of the fluid increases. So fluid decreases, but the velocity of our fluid increases. Okay? So I hope na-refresh, bumalik kayo sa pagkabata on this example. Okay, so yung gusto nyong pihitin or you want a greater what do you call this one? A greater velocity, you made the exit area of our hose smaller, so it will just give a splash than the usual exit and the usual output of our fluids. Okay, so when you are watering plants using the water hoses, if you need to shower the plants way far from your reach, you tend to close the hoses opening so that the water will spray to a longer distance. That only proves that you didn't change any water pressure, just lessen the hoses opening. By that, the water goes out faster than the normal speed. So limiting the hoses opening makes the fluid travel faster without changing the pressure the fluid exerted. Okay, so we have here hose opening 1 is equivalent to hose opening 2. We have here pressure 1 plus 1/2 raw velocity, which is mass density times velocity squared plus the rho gh. Okay. So we have here P as our pressure, Pascal. We have here the rho or the density, mass density, kilogram per cubic meter. And we have here the velocity, meter per second. And gravity of 9.8 meters per second square. And lastly, we have the height. Okay, so all of these are pressure. And those H1 opening as a pressure, as a unit of pressure. So yeah, okay. So as you can see, we have a greater pressure in here than in here. Okay, but what happened here is that the velocity is much greater than our the velocity of the on the end or in the opening of the hose is greater than the velocity of our from our inlet. Okay, ayan. So wider diameter than this one, but the velocity will be much greater. Okay, so yeah, so let's try to solve for this one. So this first example, so we have here a reservoir glycerin has a mass of 1200 kilogram or 1200 kilogram and a volume of 0.952 square cubic meter. So find the glycerin's weight, mass density, specific gravity, specific weight, and specific gravity. Okay, so let's try to solve this one, guys, and I hope na maging okay ang ating pagsasagot. So please try to solve this one. Okay, so I'll be leaving this to you. So please try to solve. So, okay. So, let's try to solve for this for the weight of the glycerin. So, first one, we have the weight, which is mass times the acceleration. So, we don't have any acceleration. So, we will be using the gravity instead. Okay, so since it is not running, so the glycerin is not running or it doesn't provide any motion, so we can assume that this one is at rest. So if it is at rest, the acceleration that we will be using is our gravity. Okay, so we have here weight is equals to mass times the acceleration, or in other terms, or in other we will be substituting the value of our 1,200 kilograms multiplied to our 9.8 meters per second square, which will then result to 11,760 newtons. So let's try to solve for this 1,200 times the 9.8. We will have 11,760 newtons of weight. Okay, so we have solved for our weight. Now we try to solve for our mass density. So we have here mass density, rho is equals to mass all over the volume. So we have here our mass, which is 1,200 kilogram, and the volume of 0.952. So 1,200 or 1,200 kilograms divided by 0.952, we will be having a mass density of 1,261 kilogram per cubic meter. So let's try to solve this one again. 1,200 divided by 0.952. So we have here 1,260.5, but we just rounded up into 1,261. So in case like this, what I mean case like this is just for the lecture, we just rounded up into the nearest 100. So, but in examinations, we will be still using the 2 decimal places. Okay, so 2 decimal places pa rin tayo. Okay, so let's continue, guys. We have to solve for our C, or our specific weight. Specific weight, weight all over volume. So we have weight, we can use weight na, which is 11,760. Okay, so yan. So we have here the weight of 11,760 newtons, or divided by 0.952. We will have an answer of 12,352. 11,760 divided by 0.952. We have an answer of 12,352.94. So yan, typographical error. So this will be 12,353. Okay, so 12,353. Okay, so another method of solving our specific weight is our rho times gravity. So let's try to solve this one using our rho and gravity. We have a rho of 12,061 multiplied to 9.8. Oh yeah, okay. So it's a little they have a little discrepancy. Okay, so but they have a little discrepancy of 4.8. Okay, so let's try to use 0.5. Yeah, okay. So as you can see, we use the original value of our mass density. So we use the original value of our mass density, which is 1,260.5 multiplied to our gravity, which resulted to 12,353. Okay, so malapit yung naging sagot. Okay, so this is the power of using the original value rather than the rounded up. Okay, so this is the power of those cases. Okay, so that's why we will use the value of our using the value of our values, yung walang putol, meaning we will be using the value as it is. Okay, so if you're just going to place your answers, two decimal places, okay. And if it is two decimal places for our final answer, we will be using the original value, walang putol, kapag sa ating other components that involves final answers. Okay, so involves other components pa. Okay? So let's move on to our specific gravity. Substance of the uh, gamma, or the specific gravity of but the specific weight of our glycerin and specific weight of the water. Okay, so specific weight of the water is 9.8 Newton per cubic meter. So since it relies on our gravity. Okay, so we have here SPGR of 1,260. Okay, so 12,353 na divided by 9.8. So we have here the answer of, okay, so 1,260.5 or 1,260 point 1,261. So okay guys, so I hope you understand or you get all these answers. So you get all these answers because this is not the end. So this is just the first example, and if you want, please try to copy this. Okay, so I'll be giving you ample time to copy this one, and we will proceed to the next example. Okay, so please try to copy this one. Thank you, guys. Okay, so let's proceed to our next example. Okay, next example, please. Okay, so solve for the absolute pressure of a water in the top of a house at a height of 15 meters. Okay, so guys, 15 meters, absolute pressure. Pressure with height, so alam nyo na siguro. Bibigyan ko na yung tip, Rho GH. Okay, so please try to solve this one, guys. So, okay. So, solve for the absolute pressure. So, of a water in the top of a house at a height of 15 meters. Okay, so, P abs, P atmospheric is equal to gamma times the height. So, we have atmospheric pressure of 101,325 of Pascal. So, we have atmospheric pressure of constant, which is yung 1 atmospheric pressure natin from our previous lesson, like yung ating measurements. So we have here one atmospheric pressure of 101,325 Pascal plus 9,800 Newton cubic meter of the specific weight of water. The specific weight of water of multiplied to our height of 15 meters. Okay, so hindi pala magagamit dito yung ating Rho GH since wala tayong mass density and gravity wala naman, pero yung mass density natin wala eh. Okay, so yun. So we will be having a absolute pressure of 248,325, or in other terms 248,000 kilopascal. Okay, so let's try to solve this one. 101,325 times plus. Okay, 9,800 multiplied to 15 meters. Okay, so we have here the 248,325 Pascal answer. So we have solved the value of our absolute pressure at the top of the house. Okay, so yeah, let's proceed to another example, which is the example number 3. So Pascal's principle. So solve for the applied pressure for a bus to move up. Given the bus has a weight of 5,000 newtons over the platform and of 30 square meter area. Okay, so the area of the pressure applied is 2 meter squared. 2 square meters. Okay, so let's try to solve this one, guys. Okay, so please try to solve this one. Ito yung Pascal's principle natin. FA over AA is equivalent to FB all over AB. So please try to solve this one. Okay, so here is the third example, Pascal's principle. So solve for the applied pressure for a bus to move up. Given the bus has a weight of 5,000 Newton over the platform of 30 square meters. Area of the pressure to apply is 2 square meters. So let's try to solve this one. So we have here pressure 1 is equivalent to pressure 2. So F1 over FA over A1 is equivalent to F2 over A2. So substituting all these values, we have here 5,000 newtons divided by 30 square meters. It's equivalent to F2 all over 2 square meters. So F2 is equivalent to applied force should be 300 uh, uh, 333 newtons. Okay, so let's try to see this one, solve this one. Okay, so let's try to solve this. Okay, so we have here 5,000 divided by 30, which is equivalent to um, x. So this is our unknown, and the unit or the area that has applied is 2. Okay, so let's try to solve this one. 333.33. So may palabis pa. So if you guys don't know how to use this ship solve, so you can use this one. So if you don't know, we can transpose it, or so we can use this method. So 5,000 multiplied to 2, meaning cross multiplication, divided by 30, which will then result to 333.33 newtons. Okay? So, sige guys, I'll be giving you ample time to copy this one, and then we'll be proceeding to the next slide. Okay? So, let's try to please copy this one. Okay? Okay, so let's proceed to our next example. Okay, so for water at a gauge pressure of 3.8 atmosphere at street level flows into an office building at a speed of 0.06 meter per second through a pipe of 5 centimeters in diameter. So the pipe tapers down to 2.6 centimeters in diameter by the top floor, 20 meters above. So calculate the flow velocity and gauge pressure in such a pipe on the top floor. Assume no branch pipe and ignore viscosity. Okay, so no branch pipe and wala tayong malapot uh, na fluid. Okay, so let's try to solve this one. So please guys, try to brainstorm for this one. Medyo tricky siya. So this one is Bernoulli. So this one is Bernoulli yung ating may velocity. Okay, so please try to solve this one, guys. Okay, so let's try to solve this one. So we have here, using continuity equation, so V2 is equivalent to A1 V1 over A2. So we have here pi 0.5 square all over 4 multiplied to 0.06 meters per second divided by pi, um, 0.026 squared all over 4. Okay, so we have here the velocity 2 of 0.22 meters per second. So, and by Bernoulli's principle, P1 plus 1 half rho velocity 1 square plus rho gh is equivalent to P2 plus 1 half rho v squared plus rho gh. So substituting all those values, the we will be having the pressure of so we will be having here the assume calculate the flow velocity and the gauge pressure. So we just solve for our velocity and our pressure. Okay, so yan. Okay, so if you have any questions, guys, so feel free to ask questions. So medyo maikli lang yung ating example, yung ating lesson ng fluid mechanics, but medyo siksik, mahirap, medyo unpredictable siya sa paggamit ng mga formulas. So I hope guys na maging okay at maging maganda ang kalalabasan ng inyong pag-aaral for this specific lesson. So if you have questions, guys, so please raise your hands or you may ask questions. Okay, so yun guys. Okay, so please uh, watch this over and over again for para mas makuha ninyo, mas maintindihan ninyo yung concept and yung lesson natin about this fluid mechanics. So, okay guys. So, yun lang. Peace out guys. Bye.